Hello everybody. Today I've got for you some tips on how to kind of research and start thinking about the design for your seismic model. Okay, so the first part of this is from a professor down at the University of Illinois that I reached out to, and he was able to send along some general tips from a point of view of an engineer and what they kind of look for structurally when they're designing a building. The first thing is looking at what goes into designing the building overall is you've got this owner that's going to pay for the building. So in our competition here, that I guess going to be me, and then you guys are going to do the designing of that structure. The main purpose of any building owner is they want to make money, right? So it's going to be they want revenue coming in, and to get that revenue, they have to have a facility or a building that will draw people to live in or businesses to bring their businesses to reside in. So stuff like having rentable space with good rooms, with windows, and also if we're looking big corporation wise, this is why big cities have these, is you want it to be tall. Okay. If you don't meet that criteria, you're just not going to make money, and it's not going to be a good investment for that owner. So to design this building, you've got an architect, okay, and you guys, when you do this, it's going to be kind of a team effort. Okay, so when you're trying to come up with the look of the building, that's going to be kind of the role of the architect. And the architect is looking to meet the owner's needs. So in our case, we're going to be building the structure someplace that is earthquake prone, so it has to be able to withstand earthquakes, but we also want it to look nice as well. So you guys are going to, the school, students and faculty are going to vote on your buildings to determine which one is the most aesthetically pleasing. The winning group or the groups of that are going to get a bonus to their revenue. So you're going to earn more money the better looking your building is. Okay. And so there's lots of different avenues or ways you can go. So just, when you're coming up with kind of the architectural concept, feel free to think outside of the box, because that's how we end up with buildings like this one here in California, as well as overseas. All right, so building a structure that is going to be able to handle structural loads. Now there's different loads that can be applied. Gravity, okay, so I'm going to be attaching weights to your building that will be applying a force onto your building. In the real world, you've got earth and water pressure, wind blowing. Those are things we're not going to have. And then what we're dealing with is earthquakes. So we've got our earthquake table, our shake table that we'll be using to apply that. So you guys should have gone through the process, or you will go through the process of looking at this model to kind of play around or think about how, if you've got some type of load or stressor force applied to a structure, how does that get transmitted through the building down to the ground. Okay, so structures are going to respond to these loads. Okay, so the weight that's applied to your building for your model, the earthquake that happens, and then it's going to shake, it's going to move. The goal for you is to have it not fall or fail. Okay, so this is showing just a diagram of, in a real building you've got wind, so it's going to be stronger winds up towards the top, hence the larger force vectors. You've got the weight of the people, so we're going to be attaching weights onto your structure to represent that. Earth pressure we're not going to have for our model, other than we're going to clamp your building down to the shake table, and then the earthquake itself, which is going to be represented with our shake table. Engineers, so that's architects doing the design. Engineers are the people who are looking to design this building to make sure it doesn't collapse. So the engineers are the ones that are going to look at the forces and make sure that it's constructed in such a way that it will be able to withstand an earthquake. So a small office building is more dangerous than a tall skyscraper. Okay, now that's generally true, and the reason why is the taller the structure is, the more flexible it is. Okay, so when it's more flexible, the less energy is required to keep it from toppling over. So when you're building your structure, you want to kind of keep that in mind. If you have a building that's really rigid, one of two things can happen. One, it will be too rigid and it'll break. Two, it won't break, but it will transmit all of its force from the earthquake directly into the contents of your building. So a little bit of flexibility in your building is not a bad thing. Generally, it's a good thing. Engineers look for that to try to dissipate some of that energy. Okay, and the analogy to here is if you're on a bus or a subway, you know, it's tough if you notice to stand, um, but it's requires less effort. Okay, if you flex your body a little bit and let your body kind of go with the bumps and the jolts. All right, so here's some hints for you. Your ground floors should be sturdy, okay, because you have all of this mass above the ground floors. So that means that the ground floors are going to be exposed to the greatest amount of force. So you want to make sure your ground floors are sturdy. Avoid weak links, okay? So when you're building your structure, as you go up from the bottom up to the top, just try to, you know, maybe not this design, this would be a really bad idea. But when you're, you know, putting stuff together, really try to think about how the forces are going to be transmitted through your building. Don't be top heavy, okay? And that kind of goes without saying because the shake table, the earthquake's going to happen down here, and if you have all this mass up top, you know, it's going to be more prone to fall. All right, construction. Again, these are all roles that you guys are going to be sharing, but the builder is the one who's actually building it. And when you're building it, here's kind of my tip for you is just make sure that you're attaching everything firmly together because the connections are really important in any building, and even in our models. Keep in mind though that you're in our model building, you are not allowed to use excessive glue. So you can't have just glue pouring all over the place because that'll be a violation and you're going to lose money or revenue because of it. So generally speaking, a frame building, now you don't have to do a frame building, it's totally up to you what you want to do, but you're going to have, you know, beams are typically going to be present and these columns, that's kind of the base structure, and they make up what's called the frame of the building. Some buildings will have skin and glass cladding. We are not going to be doing that for our lab. But you can see here is that you've got your columns and beams, and then you've got your cross structures, and that has to do with trying to dissipate or spread that load from the earthquake through the building. So not, because again, you're trying to avoid having too much stress or force being applied at one joint because that will lead to that joint failing. Here's a John Hanke, which is, again, most people have seen this, but it's a cool architectural effect, but also it has a structural purpose as well. There's some other famous, well-known buildings. All right, so pre-build, really what are you looking for? So title page, it's pretty self-explanatory. Problem and purpose. So this is where you want to look at the beginning of the packet where it talks about who the owner is, what they're looking for, where you're building the building, what is the purpose for your team, and again, focus here on being professional and creative, and that's how you're going to get this maximum points right here. Alternate design and design process. Okay, so for this one, this is where you're going to flesh out, you know, designs that you thought about doing but decided not to do, or think of it this way, just, you know, this is why I would not do it that way. Okay, so some type of computer generated designs or images with key features identified. Okay, so it can be if you want to draw something and scan it in, that's fine. Again, it's all going onto the Google Classroom document. And then lastly, description of structural engineering concept and design. So this is where you're going to show me that you are thinking about the actual design of your building, that you're not just randomly gluing balsa wood sticks together, that you have a purpose in what you're doing. So again, that can be a computer generated design or a well-drawn design. You don't have to do your whole building if you just want to do some, you know, key features to it. So you just got to put a little, your group has to put a little thought into this on how you're going to do it. And again, you will be able to edit this. So I'm going to kind of give you some tips and pointers after you're done with this, and I'll send it back to you for you to be able to make edits too. Okay. Now where to start research-wise, the EERI Seismic Design Competition, that's the undergraduate college version of what you guys are doing. So there's obviously very intense, because they spend all year building these things, but it may give you some ideas looking to see what the undergrad engineering students are doing at the collegiate level. Okay, and if you look up Google search earthquake shear or lateral force torsion, those are some of the physics words that engineers are going to be using when they design buildings. So that might be something you want to look at too. And then also static analysis for lateral forces. Again, even if you pull up a couple of YouTube videos, they'll give you some ideas on some concepts that you can try to apply to your model. Here's a video that kind of walks through some of those concepts. At the end of the video, that'll be the completion of this presentation. If you need any help or guidance, just shoot me an email or stop me in class.
To understand the resonance of buildings during earthquakes, we will look at other resonance systems. The natural frequency of a swing makes it easy to maintain the motion using little energy. A prolonged wind swung the bridge on the right at its natural frequency until it exceeded its structural integrity and tore apart. The frequency of a wave refers to the number of waves that pass through a point in 1 second. A period is the amount of time that it takes one wave cycle to pass the given point. A frequency of 1 cycle per second has a 1 second period. If the frequency doubles to 2 cycles per second, the period is only half of a second. Resonance is a tendency of a system to oscillate with greater amplitude at some frequencies than at others. The resonant frequency of any given system is the frequency at which the maximum amplitude oscillation occurs. For example, the resonant frequency of the 1 meter long pendulum is 1/2 of a hertz. If the string were 1/4 the length, it would vibrate at twice the frequency. Small amplitudes can be approximated by this equation using length and the gravity constant. Resonant systems can be used to generate vibrations of a specific frequency to create music. Strings under tension, such as with this cello, have resonant frequencies directly related to the material of the string as well as the mass, length, and tension of the string. The mass of the slow C string resonates at 264 Hz, whereas the thinner A string of a different material resonates at 440 Hz. Now, we use a simplified analogy of boats at sea. A series of waves, particularly when they hit broadside, can initiate rolling behavior. The smaller boat is affected by short-period low-amplitude waves that slap against the ocean liner with no effect. Small boats, on the other hand, will ride up and over long-period high-amplitude waves as the larger boats begin a long, slow rock. Now, let's look at how buildings are affected by earthquake-induced seismic waves. All buildings have a natural period, or resonance, which is a number of seconds it takes for the building to naturally vibrate back and forth. The ground also has a specific resonant frequency. Hard bedrock has higher frequencies than softer sediments. If the period of ground motion matches the natural resonance of a building, it will undergo the largest oscillations possible and suffer the greatest damage. Small buildings of 1 or 2 stories resonate naturally at much less than 1 second periods. A 1 second period will affect buildings of about 10 stories. For example, a 30-story building resonates at a period of 3 seconds, and a 50-story building resonates at a period of 5 seconds. During the 1985 Mexico City earthquake, the ground beneath the city resonated with a 2-second period for over a minute. Thus, medium-height buildings with similar natural periods suffered the most damage, while short, old, weak stone buildings and skyscrapers were relatively undamaged. That proved to be what is called a resonance disaster, which is how engineers describe the destruction of a building by seismic vibrations at a system's resonant frequency. It is because of prolonged energy input that the system swings more and more strongly until a structural load limit is exceeded. A key point here is that small buildings on hard rock and large buildings on soft sediments may suffer more damage and ground motion effects from an earthquake than small buildings on soft sediments and large buildings on hard rock. Resonance is one factor that contributes to earthquake damage. Of equal or greater importance are building design and the quality of construction materials. By determining the resonant frequency of the ground beneath the building site, the building design can be modified so that a resonance disaster does not occur. The following demonstration shows how to model resonance in the classroom.
The idea of the BOSS model is that different height buildings will respond to different frequencies of horizontal ground motion. A tall building will respond to very slow or low frequency oscillations of the ground. So if I move the base slowly back and forth, I can get the tall building to oscillate, where the intermediate and short buildings are not moving. If I move it more briskly, I can dial in the rate of horizontal oscillation so that I move the center building, the intermediate height building, and the short and the tall ones are barely moving. To get the short building to oscillate, you need to move the base very briskly back and forth and dial in to the natural frequency of the short building, and we can see that the intermediate and tall buildings are barely moving.
House built on a weak foundation will not stand, oh no.